So in traditional fluorescein angiography, you obviously inject a fluorescein dye, and you can see my right eye as it's visualized in the fluorescein. You see the major vessels, but you don't see a lot of the deeper plexus. And that's a very, very important issue. Now, if you look at the same eye, my right eye, looked at with OCT angiography, you can see the same major vessels, but you can also see the intermediate and the deep plexus of this vascular tree in one image. And obviously, it only takes a couple of seconds instead of several minutes to make such an examination. Now, how does it work? Now, if we, for example, wanted to take and make an OCT angiography of this vessel right here, our algorithm takes that scan and does it 4 times very, very fast over the same position. So what we have is we have 4 images going over the erythrocytes and the vessel wall, and it makes these 4 images. Then it takes these 4 images and does a subtraction analysis, and what we see is everything that moves, which is the erythrocyte, stays there, and everything that doesn't move, which is the vessels, disappears. So what we're seeing is a subtraction analysis, and we see all the moving particles. So this explanation is relatively straightforward. But I noticed very early on that even this explanation doesn't really help people understand how this works, and especially not how OCT artifacts work, or OCT angiography artifacts. And I noticed this in my last meeting, the OCT angiography retina meeting in Rome last year. So what I did in order to clarify this is I went to the Trevi Fountain in Rome and took a look at it. So I took my iPhone and I put it on the side of the fountain, and I wanted to see if it was possible. Could I make an OCT angiography of the Trevi Fountain? And the way you do that is you take a film, then you copy the film, and you subtract one frame from the film, and then you subtract the first film from the second film. And everything that remains still, like the horses and the fountain itself, will be subtracted out of the image, and everything that is moving will not be subtracted out of the image. So what does this mean? What happens when we then do the subtraction analysis is that it looks like this. And this is, in essence, an OCT-A, an OCT angiography of the Trevi Fountain. So you've got the larger vessels here, and you've got the smaller capillaries here. But it's still too much movement, so we sum that image, and this is what you get. So here you've got larger vessels, and here you've got capillaries. And in essence, this is exactly the way that OCT angiography works. And understanding this is pivotal for your being able to interpret OCT angiography images correctly. But what about projection artifacts? How do they work? So in order to visualize that, I went to the Five Rivers Fountain on the Piazza di Navona at night. And what we see here is, here we have a light, a street light, and here we have the moving water, and the light goes through the moving water, and it flickers on this lion's head and on the fountain itself. So here you've got the fountain. Let's say that's the RPE. Here you've got this lion head. Let's say that's a fibrosis on the RPE. Here you have a vessel, and the light is the OCT laser source. Now, as you can see, this movement causes a flickering on this highly reflective surface. So when you do a summation, this is what happens. You see the movement of the vessels, of the erythrocytes, and you see flickering on the RPE and on the fibrosis. Now, when you do a summation of that, this is what you see. And this is exactly what you might be able to see if you have a fibrosis on the RPE or any kind of highly reflective surface on the RPE, and you see vessels in it. You need to first check, are there vessels above it that have exactly the same look? Because this is how they're caused. So you need to be aware of this artifact and understand where it comes from in order to be able to correctly interpret OCT-A.